In 1896, Henri Becquerel discovered that uranium spontaneously emitted a mysterious X-ray-like radiation that could interact with photographic film. Curie soon found that the element thorium emitted similar radiation. Most importantly, the strength of the radiation depended solely on the element's quantity and was not affected by physical or chemical changes. This led her to conclude that radiation was coming from something fundamental within the atoms of each element. The idea was radical and helped to disprove the long-standing model of atoms as indivisible objects. Next, by focusing on a super-radioactive ore called pitchblende, the Curies realized that uranium alone couldn't be creating all the radiation. So, were there other radioactive elements that might be responsible? In 1898, they reported two new elements: polonium, named for Marie's native Poland, and radium, the Latin word for ray. They also coined the term radioactivity along the way. By 1902, the Curies had extracted 1/10 of a gram of pure radium chloride salt from several tons of pitchblende, an incredible feat at the time. Later that year, Pierre Curie and Henri Becquerel were nominated for the Nobel Prize in Physics, but Marie was overlooked. Pierre took a stand in support of his wife's well-earned recognition. And so both of the Curies and Becquerel shared the 1903 Nobel Prize, making Marie Curie the first female Nobel laureate. In 1911, she won yet another Nobel, this time in chemistry for her earlier discovery of radium and polonium, and her extraction and analysis of pure radium and its compounds. This made her the first, and to this date only, person to win Nobel Prizes in 2 different sciences. Professor Curie put her discoveries to work, changing the landscape of medical research and treatments. She opened mobile radiology units during World War I and investigated radiation's effects on tumors. However, these benefits to humanity may have come at a high personal cost. Curie died in 1934 of a bone marrow disease, which many today think was caused by her radiation exposure.
Each element comes in a number of different forms, called isotopes, each of which has the same number of protons, but a different number of neutrons. Importantly though, only 1 or 2 of an element's isotopes are stable, while the rest of them are unstable, and so can undergo radioactive decay, which is where they emit something so that they can change slightly and become more stable. So when we say that a material is radioactive, all we mean is that it consists of unstable isotopes that can decay. Let's start with alpha radiation. Alpha particles are made up of 2 protons and 2 neutrons, which is exactly the same as the nucleus of a helium atom. So we normally represent alpha particles with helium's nuclear symbol, He. Importantly though, alpha particles don't have any electrons, so they have an overall charge of 2+ from those 2 positive protons. Because they are relatively large, alpha particles are easily stopped by collisions with other molecules, which means that they can't penetrate very far into other materials. In fact, they can only travel a few centimeters in the air, and are absorbed by a single sheet of paper. However, their large size and their strong charge does make them very strongly ionizing, which just means they can easily knock electrons off any atoms that they collide with. Next up, we have beta particles, which are just electrons. So they have a charge of -1, and virtually no mass. Now, the weird thing is that electrons aren't emitted from one of the atom's shells. Instead, one of the atom's neutrons decays into a proton and an electron. The proton stays in the nucleus, but the electron is emitted out at high speed. Because beta particles are pretty tiny, they are moderately ionizing, and they penetrate moderately far into materials. For example, it would take several meters of air, or about 5 millimeters of aluminium to stop them. Now, gamma rays aren't particles at all. They're actually waves of electromagnetic radiation, like light is. And they're often emitted after alpha or beta radiation, as a way of the nucleus getting rid of a bit of extra energy. As they don't have any mass or charge, they tend to pass straight through materials, rather than colliding with any of the atoms, which makes them only weakly ionizing. This means that they can penetrate really far into materials before being stopped, so it can travel long distances through air, and it takes thick sheets of lead, or multiple meters of concrete to stop them. So when an unstable nucleus, like uranium-238, undergoes alpha decay and emits one of these alpha particles, it's going to lose 2 protons and 2 neutrons. To show this, we have to subtract 4 from its mass number and 2 from its atomic number. So uranium-238 would go to form something with a mass number of 234 and an atomic number of 90. Because the atomic number has changed, it will now be a different element. So we'd have to check the periodic table to find out that it's now thorium. The last thing is to add our helium that was emitted, and then just double check that the mass and atomic numbers on each side of the equation are the same overall. Now, beta decay is a bit more complicated, because it involves a neutron turning into a proton and emitting a fast-moving electron, which is the beta particle. So if carbon-14 was to decay and emit one of these electrons, then because it's effectively gained a proton, its atomic number would increase from 6 to 7, making it nitrogen rather than carbon. However, its mass number would stay the same, because although it's gained a proton, it also lost a neutron, so still only has a total of 14 protons and neutrons in its nucleus. Just like with the alpha particle, you can also represent the beta particle with an actual beta symbol. But either way, we have to put a -1 at the bottom to show that it has a charge of -1, and a 0 at the top to show that its mass is pretty much 0.
Gamma radiation can be used in radiotherapy for the treatment of cancer. Gamma radiation is directed at the area of the body affected by cancer. At high doses, radiation kills cancer cells or slows down their growth by damaging their DNA. These dead cancer cells are broken down and removed by the body. Radiotherapy doesn't work straight away. The cancer cells can take up to a few months to die and be removed by the body. Radiotherapy can also be used to destroy other tissues in the body that are not useful. For example, radiotherapy is often used in the treatment of overactive thyroid glands. If the thyroid gland produces too much thyroxine, it can result in heart palpitations, anxiety, tiredness, and mood swings, amongst other symptoms. Radiotherapy can be used to destroy some cells of the thyroid gland and thereby reduce the amount of thyroxine that is produced. Beta and gamma radiation can also be used as tracers. Tracers in the body can provide a useful alternative to surgery. A small amount of radioactive material is introduced to the body, and a radiographer follows the passage of this material through the body using specialized equipment. Beta and gamma sources are used because they pass out of the body and so can be detected. Remember, alpha radiation can't travel through anything thicker than a sheet of paper. Barium meals or barium enemas are common examples of radiation used in this way. Radioactive tracers are also used to find leaks in water pipes. Smoke detectors emit a constant stream of alpha particles. A sensor continually detects these alpha particles, causing a small current. If smoke particles come between the source and the detector, the current is decreased and an alarm goes off. Gamma radiation is used to sterilize hospital equipment and is also used to kill bacteria, mold, and insects from food before the food is packaged. This increases the shelf life of the food. The food is safe to eat and doesn't become radioactive itself, as it's irradiation rather than consumption. Irradiation is when a person or object is exposed to radiation without coming into direct contact with the radioactive source. The person doesn't make direct contact with the radioactive barrel, but since irradiation can happen at a distance, the person is still at risk. The damage to the person only happens when the person is in the area of the radioactive waste. Therefore, the person is only exposed to the radiation for a short time, and so receives a low dose of radiation. Contamination is when a person actually comes into contact with the radioactive wastes. The person takes the radioactive source away with them, and so are exposed for a longer period of time, and consequently have a higher dose which can lead to more damage. Contamination can happen in a variety of ways, from picking up a source, to breathing it in, and to ingesting it.